Well, you did it. You push your chat app to production. The UI is clean, the message is sent, and you're feeling like a 10x engineer. But then the absolute worst case scenario happened. 1 million users actually showed up. Spoiler alert, it didn't just lag. It caught fire. Most developers think scaling is just a matter of adding more RAM. But at 1 million concurrent connections, the law of physics and operating system limits start working against you. Welcome to a system design deep dive where we analyze the flaming wreckage of a naive development and rebuild it into a global powerhouse. Today we are architecting a system that won't melt. We are aiming for the holy grail of infra. 1 million live WebSockets, 500 million messages a day, and P99 latency under 100 milliseconds. If you have ever wondered how WhatsApp or Telegram handle billions of messages without breaking a sweat while your local dev server crashes with 10 users, this is for you. It's a 10-step descent into engineering madness. We are going to walk through the roadmap one concept at a time. We are starting with N-squared problem, the silent killer of chat apps. If you don't understand how message broadcasting works, your app is essentially a self-inflicted DDoS attack. Then we are talking about the data layer, where you cannot just select a star from a table with a billion rows and expect a response this century. Then we are going to dive more deep into Kafka and Redis, about the fast path, about durable paths, and finally we are going to assemble a full 7-layer architecture. This is going to be a blueprint used by top 1% of apps to maintain 99.99 uptime. Okay, let's look at the happy path first. At launch stage, we maybe have 500 concurrent users. The UI is snappy, latency is beautiful, 8 milliseconds, and our single WebSocket service is chilling at 12% CPU, as you can see it here. This is where most tutorials end. They tell you, congrats, it works. Now, let's add some more pressure. If we are growing at 45k users, the foundation starts to crack. That lone WebSocket server is now at 85% capacity. The P99 latency is creeping up to 60 milliseconds, and you might start seeing connecting spinners and so on and so forth. But as you can see here, the latency is even way more than 60 milliseconds. So the crash looks something like this. The server process hits its file descriptor limit. The event loop is blocked. Memory is swapping back and forth, and to the user, the app is just dead. Notice the error rate. It's at like 100% and climbing. So this is where most startups die. They are the victim of their own success because they didn't architect the next order of magnitude. So how do we fix it? We don't just buy a bigger server or buy more RAM. We change the game entirely. So let's look at 6 specific challenges we have to solve first. Okay, for starters, the challenge 1, the N-squared problem. If you have 1,000 people in chat room and one person sends a message, you have to push that message to 999 other people. That makes 1,000 operations. If everyone talks at once, that's 1,000 squared operation. At 1 million users, you're talking about 1 trillion operations. Your server isn't a server anymore. It's a space heater. For the challenge number 2, the fan out. When a celebrity sends a message to, let's say, 50,000 people, you can't do that sequentially. If each send takes only 1 millisecond, the last person gets the message 50 seconds later. That's not a chat, that's a letter. We need massive parallelization to solve the thundering herd problem. At number 3, we have the database. A million users generating 5,800-ish writes per second. Your standard MySQL or Postgres instance will lock up under that write pressure. Yeah, the next one is state. Unlike REST, where you can hit any server, WebSockets are sticky. If user A is connected to server 1 and user B is on server 2, how do they talk? We need a state provider like Redis so that it can act as the switchboard connecting these isolated islands, because as we said before, WebSockets are sticky. You cannot just randomly send messages to any servers. And the next stop is scaling gap. This is the jump from one server to 20. Now you have to worry about service discovery, load balancing, and split brain scenarios where servers lose track of each other, because this is where the complexity truly explodes. And last but not least, the ordering. In distributed system, time is a lie. If I send how are you and then hello, and they hit different servers, they might arrive in the wrong order. We need snowflake IDs or vector clocks to ensure the conversation actually makes sense. No one likes to read a chat from future, right? So how do they do it? How do big actors do it, right? So we have multiple categories to cover, but essentially, when you look at WhatsApp, they are the master of minimalism. They use Erlang, a language designed for telcos, and they delete your messages as soon as they are delivered. By not storing your history, they avoid the massive storage scaling problem entirely. This is brilliant, right? But it is a product choice as much as an engineering one. Telegram takes the hard mode route. They offer infinite cloud storage. To do this, they had to build their own custom database, Telegram DB, because nothing off the shelf could handle their specific needs for that. So they chose hoarder strategy, which requires a much more complex caching layer. The takeaway: your architecture is driven by your product. If you want infinite history, you pay for it in complexity. If you want speed, you pay for it in data volatility. So choose your poison wisely. But next, let's look at a scale simulator. How about that? Right now, we are looking at 1K user mark. Everything is green. We've got a single WebSocket node, a single Postgres instance, and we're only spending around $3,000 per month, right? Yeah, so this is what we call a honeymoon phase. Your P99 is crisp at, let's see, yeah, the message per second are 50 message, and your P99 is 35 millisecond. SLA is really good. Everything is good, right? But look at the latency breakdown chart. Even at 1K users, the WebSocket processing and DB writes are starting to claim their territory. You might think, hey, if it costs 3K for 1K users, surely it's just linear scaling from here. But no. It's not going to be that. So if you look at here, I'm going to talk about it later on, but around 50K we are hitting one node capacity, as we talked about the file descriptors. Look at the estimation cost right now, and please be aware of DB writes and our P99, which is going to look like we are sending a letter instead of doing a chat, and boom, yeah, we are doomed, right? But hey, if you look at the active infrastructure from where I started, you'll see a graveyard of grayed out tech. Nginx load balancers, Redis, Pub, Kafka, the simulator says that they're not needed yet. That is a polite way of saying your current architecture is a ticking time bomb. You're running on a single DB shard, right? But if one bad query or one heavy broadcast or one viral tweet, and that 3K bill is going to be the least of your problems. If we slide, you can see that new infrastructure or new tooling will be needed as we increase the concurrent users or concurrent connections. We are going to talk about Kafka and Redis and our DB choice and sharding it in a second. All right, so next stop is WebSocket architecture. As we said it before, WebSockets are sticky. You cannot just fire and forget. This is where the magic of real-time communication meets the reality of stateful connections. Unlike standard HTTP, you cannot just throw a request at a server and forget about it. These connections are high maintenance relationships. They need to stay open. They need constant heartbeats, and if one side stops talking, the whole thing falls apart. So yeah, to handle 1 million active connections, we have moved to horizontally scaled fit. We are aiming for about 50K connections, as we talked about it. So why 50? Again, because at that point we are usually fighting the Linux kernel over file descriptors and memory overhead and memory swaps more than you are fighting your own code. So that's our mark for adding a new node, as you can see here. But here's the puzzle. If user A is connected to server 0 and user B is on server 3, how do they talk? They are essentially in different zip codes. That's where the Redis Pub sub comes into play, right? It's a glue where it tries to send a message. So when a user A, let's say, send a message, server 1 shouts it to Redis, and server 3, which is subscribed to that channel, picks it up, whispers it to the user B. It's an elegant solution, but it means your Redis cluster better be fast, or your real-time chat is going to feel like mailing wording, right? So that's one thing. And notice the IP hash sticky session on the Nginx load balancer. We are forcing users to stay glued to the same server they started with. It's not because we are sentimental or something like that. It's just because re-establishing 1 million TLS handshake every time a load balancer decides to round robin is a great way to turn your CPU into space heater, as we talked about it before. And that's a very short but super important Nginx config to create sticky routing with IP hash. So let's talk about the fan out. If you take a look at this, a message is sent to a room of 10 subscribers. Look at the render, the millisecond, but if we change it to 1000, it's going to be something else, right? If we try 500, but the change of order of magnitude here is 1, right? So we are going from 100 to 1000. But let's imagine that it's going to be a million subscribers. This is going to be huge. So the FANA strategy here is a pivot point. Instead of forcing the database to handle the explosion, we are going to use Redis publish again to broadcast a message to all the WebSocket servers who care about this message instantly. So here we are. This is a happy path or fast path versus a durable path, right? So to survive a million users, you have to stop treating your data like a big pile. That's why if you notice the split on WebSocket 01, this is the moment a message hits the server. It takes two separate journeys, the fast path and the durable path. Let me show it like this. Alright, so the fast path is that we fire it into Redis Pub sub. It's a fire and forget. It's built for sub-millisecond delivery thanks to Redis. It doesn't care about history, it just cares about right now. But on the contrary, the durable path, simultaneously we produce a message to Kafka. This is our safety net. Kafka handles the heavy lifting, persistence, offline delivery, and analytics. By participating in Kafka topics, by partitioning Kafka topics by room ID, we ensure messages stay in order without choking a single worker. And we finally swapped our single postgre bottleneck for Cassandra, a database that actually enjoys being hit with a million writes. So in short, Redis, Kafka, and Cassandra for appropriate amount of writes in our chat app. And here you can see a suggested way of handling it via Redis and Kafka. So here is the beauty of Monolith vs distributed system. As we talked about it, if we are talking about more than 50,000 concurrent users, one server is not going to be enough, right? So if you see it like this, yeah, after 50,000, its monolithic approach is going to be dead. But as we add more servers to our distributed system, as you can see, the load is distributed, balanced, and we are utilizing 30 to 40% of our CPU, and memory is at a reasonable amount for 1 million user. So this is the difference between monolithic and distributed, as we talked about it. But what about the database? Eventually we have to save our data, right? This is the database schema on sharding strategy, where we stop treating our database as a single box and start treating it as a distributed map. You are watching a lot of things happening at the same time in this fold, but let me talk about the right path. We are not just dumping raw text into a table. We are generating snowflake IDs, as you can see here, which is a 64-bit time sortable integers. forget about UUIDs because they are too bulky and will kill the index performance. Snowflake IDs gives you chronological order across distributed nodes without needing a central counter to tell us what time it is. To actually store petabytes of history, we use consistent hash ring. We have split our data into multiple shards, each holding about 125 million rows. And this ensures that if shard 0 gets hit with a viral group chat, shard 2 is still chilling. It's the only way to maintain a 5800 writes per second pace without disk melting. But not all data is equal. We have implemented storage tiers. So if we are talking about the last 100 messages of every room, sub 1 millisecond latency, let's be real, nobody scrolls back further than that anyway. So we are talking about Redis here. Messages from last 30 days, this is where the bulk of your active searching happens, which is going to be warm, which is going to be Cassandra in this case. But Parquet or S3 is going to be used for historical archives. If you want to find a message from 2022, we'll get it for you, but you're going to wait like 500 milliseconds for that S3 to fetch. So these are the tiers of data retrieval based on mostly their date and historical value, right? All right, so let's go on. Let's move on. So about the performance metrics, this is harshly the amount of concurrent connections each node can handle, about the throughput capacity, which you can see Kafka rules, but based on the durability vs being fast, you are going to choose either of these and hopefully not the DB write, of course. And here you can see the latency from monolithic vs distributed systems. As we talked about it, somewhere around 50,000 connections, the monolithic is going to die, especially if it's one monolithic server and not even distributed monolithic. But distributed systems are going to live longer, obviously. How about caching? So if you're still hitting the database for every read at 1 million users, you are already lost, right? Most the three-tier cache hierarchy meet the three-tier cache hierarchy. The reason 90% of your requests never even see a disk. At layer 1 or in-process cache, we have the local RAM on the WebSocket server. This is for things that need to be faster than light, like rate limit counters and session tokens. So it's sub 0.1 millisecond latency, basically instant, right? At layer 2, we have distributed cache, a more advanced and interview-friendly topic, so to say. For instance, a 6-node cluster acting as the source of truth for live data, whose online room member list and the last 100 messages. At layer 3, basically Cassandra and Postgres, this is the last resort. As you can see by the 7% database hit rate, if a request makes it this far, it's usually for something boring like an audit log or account setting change or something like this, right? And yeah, so we are using specific Redis patterns to keep this lean. SetX for presence tracking ensures that if a user's heartbeat stops, their online status expires automatically. No cleanup scripts required. We also use increment for rate limiting, because at scale someone is definitely trying to spam your API into oblivion. Yeah, that's pretty much it about caching. Now let's see it. Yeah, as you can see in this live dashboard, there are some optimizations. There are some trade-offs hitting us right now. As you can see, the P99 is not great, but the system is working. There are some nodes where you see a red line still, right? But we expect that not to happen. This usually caused by hotspots. Hotspots are things like a celebrity working on their Twitter account, and tweeting constantly. And since WebSockets are sticky, so one server or two servers are going to be hotter than the other ones, mostly because of that. And yeah, so basically a dashboard of live data of what 1 million users look like from inside. And to complete our video, let's put it all together into a 7-layer blueprint, shall we? Yeah, at the top we have our clients. They don't talk to the servers directly. They hit a global load balancer. This load balancer uses sticky sessions. It's like a restaurant making sure you sit at the same table you started at, so your WebSocket connection doesn't break. Here's the secret sauce though: the dual path pipeline. When you send a message, it hits two paths. The fast path, which is going to be Redis, as we talked about. It's built for speed, pushing the message to the recipient server in under 20 milliseconds. But the durable path is something like Apache Kafka, which is the stream event streamer. Kafka acts as a shock absorber. It queues the messages, ensure they are persisted, and feeds them into our sharded Cassandra database. If the database is slow, Kafka doesn't care. It just holds onto the data until the database catches up. But wait, what about users in Tokyo? If our servers are in New York, the speed of light alone adds 200 milliseconds of lag. That's why we use edge locations. We deploy regional clusters that are mirrors of each other, GeoDNS routes. GeoDNS routes you to the closest one, and a global backbone syncs the state between regions. This is how you get the instant feeling regardless of where you are on the planet. Yeah, that's pretty much it about it. In conclusion, let's talk reality, the cost of success. To run this architecture at 1 million users, you are looking at roughly $78,000 a month in cloud bills. You need 21 dedicated WebSocket nodes, 4 terabytes of Redis memory, and around 130 Kafka partitions. Scaling isn't just an engineering challenge, it's a financial one as well. If your business model doesn't support 7 cents per user per month, your architecture is essentially a ticking bankruptcy bomb. To manage this, you live and die by your metrics, right? 99.99 uptime, 100 millisecond P99 latency. These aren't just goals, they are requirements. If your latency spikes to 500 milliseconds, your users will leave. In the age of instant gratification, performance is the product. Alright, that's about it. Thanks for watching, guys. Stay curious, not judgmental.